All right. So what we've looked at already is the comparison of acidities of phenol against alcohol. And we could reason the characteristic differences between the acidity of phenol and alcohol, whereby there could be around 10 to the power 5 times more acidity that could be observed for phenol. And this experimental observation has been validated by accounting for stabilizing effects that are possible in the conjugate base, which is the phenoxide ion. Yeah, Josh?
So did we have to note down the equations that we wrote previously?
Which equations are you talking about?
Yeah, the one after the diagram.
The one after the diagram, as in these
Yeah.
structures?
Yeah.
No,
Yes.
we'll discuss about substituent effects now. Okay. So we'll anyways be going through all those substituents and based on their positions, we will be discussing how they should be affecting the acidity order. Okay, so we've what we've done is we've accounted for the fact that the pK values of phenol is approximately around 10, whereas the pK values of alcohols range from 15 to 16. And this 10 to the power 5 orders of increase in acidity can be attributed to the stability of the conjugate base that we made for phenol, which is the phenoxide ion. Right? Now we are going one step further to understand what happens when I put a substituent on the phenol. Do substituents affect the acidity? And if yes, how would they characteristically change the acidity constant of phenol? And we find that phenols exhibit a very, very marked substituent effect. Substituents can decrease the pK value of phenol all the way even up to 0.4 has been observed for certain phenols. Which indicates that there is a very, very marked substituent effect that is observed for phenol, in which the substituent alters the acidity constant of the phenol greatly. Okay, now we need to understand what type of substituents would result in an increase in acidity, what type of substituents would lead to decrease in acidity, and is there a position that a substituent would favor so as to bring about a characteristic change in the physical constant, that is the pK, right? For that, let's embark on the first discussion on the type of substituents. There are two types of substituents in principle. They could be categorized as electron donating substituents and electron withdrawing substituents. Electron donating substituents could typically be methyl groups, methoxy groups, etc. OH, NH2, NHCO, CH3, all those which result in enriching the electrons in the ring will act as electron donating substituents. Electron withdrawing substituents, on the other hand, will be of the type nitro, formyl, ketone, or carboxylic acid. Our concept of acidity was that any factor that stabilizes the conjugate base would increase the acidity. So factors that stabilize the conjugate base would necessarily bring about delocalization of the negative charge. And we know that electron withdrawing groups have an ability to assimilate the negative charge. They'll try to have a flow of negative charge from the oxygen atom into those electronegative atoms or groups, thereby leading in overall stabilization of negative charge. So electron withdrawing groups will stabilize the negative charge on oxygen. And if they are stabilizing the negative charge or delocalize the negative charge, they will result in enhancement of the acidity constants. Okay. And if electron withdrawing groups stabilize the conjugate base and increase the acidity, Electron donating groups would have the exact opposite effect, where electron donating groups would tend to destabilize the conjugate base. They would enrich the electrons on the oxygen atom, which is already bearing the negative charge, and therefore result in lower acidity constants. Right? So the pKa values for electron withdrawing group substituted phenols will be lower than the pKa for those phenols which are substituted by electron donating groups. Let's take some characteristic examples and see whether experimentally also the same thing is found to be true. So let me bring in some acidity constants of phenols from a table. Let's try to reason the entries on this table. Okay, let's focus on mono-substituted phenols first. You see that phenol exhibits a pK value of 10, but orthocresol, metacresol, and paracresol exhibit a marginally increased values of pKa as compared to phenol. What are cresols? Cresols are nothing but compounds that have a methyl group in addition to the OH. This class of compounds are called as cresols, right? Depending upon whether the methyl is on ortho, meta, or para position, you would name it as orthocresol, metacresol, or paracresol. And you see that for each of these three cresols, the pKa values is slightly greater than the pKa value for phenol. Right? And what is the relationship between pKa and acidity? It is inversely proportional, right? So as the pKa value increases, you can account for the fact that cresols are less acidic as compared to phenol. And you can reason that based on presence of electron donating group or electron donating substituent on the phenol itself. Look at orthochloro, metachloro, and parachlorophenol. Isn't that a classic example? I once again draw the substituted phenols, which have a chloro substituent. Is chloro an electron donating group or a withdrawing group? It's an electron withdrawing group, right? So it is expected to bring about an enhancement in the acidity constant, according to our understanding. And we see that orthochlorophenol is the most acidic, followed by meta, and followed by para. The acidity decreases in this order. Parachlorophenol is the least acidic, followed by metachlorophenol, and orthochlorophenol is the most acidic. Now you try to input the same logic into ortho, meta, and parachlorophenols. In orthochlorophenol, the electronegative halogen is present closest to the carbon atom, which is supposed to bring about withdrawal of electrons through inductive effect. As you go to metachlorophenol, the distance increases. And in parachlorophenol, the chlorine is very, very far away to induce any inductive effect onto the forming negative charge on the oxygen. So hence not only is the type of substituent useful in predicting the acidity constants, but even the position of these substituents would affect the acidity constants. So this is a characteristic example of both of those effects coming into play. Not only the type of substituents, but also the position of substituents. So eventually we'll move into the next one, which is position of substituents. So let's take a look at paranitrophenol. And because I need to account for stabilizing effects on its conjugate base, I'm going to draw the conjugate base of paranitrophenol. And I'm going to expand the nitro group. There are a few ways in which you can write the nitro group. You can either write the nitro group like this with a coordinate bond, or you can put an explicit positive and a negative charge in a normal covalent bond. Both these representations are well accepted, but I will be preferring the use of this representation because it will allow me to move electrons, because if it's a single bond, I know how to move it around basically. right? Rather than a coordinate bond, which doesn't have charges, and hence I can't account for stabilities of the conjugate base. Okay, so what have we dealt with so far? I bring the electrons in here. The electron goes to the ortho position. So I have negative charge here, double bond O, the NO2 group as it is. Then I move the negative charge around again. The negative charge moves to the para position. The negative charge moves again to the ortho position back again. And finally, the negative charge would move back to the oxygen with an alternate arrangement of the carbon-carbon bonds. Okay, here the arrangement of the double bonds is slightly different from the arrangement of double bonds here. That is how you get the 5 characteristic resonating structures, isn't it? And this was possible for just phenol as well. In these resonating structures, there is a possibility to generate one additional canonical form. Which is that canonical form? I have a negative charge next to a nitrogen atom that is positive, which is pi bonded to oxygen. So apart from moving in anti-clockwise the way it would normally if there was no substituent around, there is another way that the negative charge can be delocalized, which is that it can be brought between the carbon and nitrogen. As it comes in between carbon and nitrogen, nitrogen becomes pentavalent. Pentavalency is not allowed on nitrogen. Hence, the electrons move on to oxygen. You get an additional canonical structure that necessarily looks like this. Okay. Apart from the 5 resonating structures that you already have for phenoxide ion, presence of nitro group on the para position generates one additional resonating structure. This would have a large contribution to the hybrid, in fact. All the atoms nearly have their octet complete. Oxygen is bearing the negative charge, the most electronegative atom. So it's fairly stable and will make a large contribution to the hybrid, stabilizing the hybrid. Right? Now let's go back to the statement that we made. Greater the number of resonating structures, more stable is the hybrid. In case of phenol, we got only 5 resonating structures. When I added a nitro group at the para position, now I'm getting 6 resonating structures. 6 resonating structures will stabilize the hybrid in a much more greater fashion as compared to the 5 resonating structures for phenoxide. More the stability of the conjugate base, higher should be the acidity of the acid itself. Now, if we revisit the table, we realize that the para-nitrophenol, presence of nitro group at the para position, which increases the number of resonating structures just by one resonating structure, increases the acidity of phenol by a factor of, can I say 10 to the power 3 times? There is a 1,000-fold increase in acidity just by increasing one resonating structure. Right? Okay, let's move back to the resonating structures. And I think by now it must have become clear to you that the negative charge does not appear on the metacarbon atom in any one of the canonical forms. Do you see that? There is no negative charge here. There is no negative charge here. No negative charge on either of these 2 carbon atoms. No negative charges, no negative charges. So in none of the canonical structures do you see any negative charges appearing on the metacarbon atoms. So if a negative charge does not appear on the metacarbon atom, you will not be able to generate the additional canonical structure which we could generate by moving the electrons present on the carbon atom bearing the nitro group into the nitro group. So what I'm essentially trying to say is number of resonating structures for metanitrophenol continue to remain 5, even though there is one nitro group in the molecule.